So
Perfect. 7.3 hypothesis for the mean while sigma is unknown. First of all, remember that in 7.2, you learned that how to form a hypothesis test while the mean of the population is given and standard deviation of the population also given. So take a look at 7.2. Let's download the file, save the file, and open it here. Let me share the screen with you. Perfect. To form hypothesis tests, we have to follow and find keywords. If you have less than, it means that you have a left-tailed graph. If you have greater than, it means that you have a right-tailed graph. And if you have not equal to, it means that you have a two-tailed graph, like this case here. So remember that when you have mu and sigma, when the standard deviation of population is given, we have to find the standardized test statistic, which is z equals to x bar minus mu divided by sigma over square root of n. Then we need to find the p-value depending on the type of graph that you have. Then you decide if you reject or fail to reject the null hypothesis. Now I expect you to ask, what if sigma or standard deviation of population is missing? What should I do now? In this case, instead of using a z value, you're going to use a t value, a standardized test. Very well. Let us go over the guidelines. To find critical values in a t distribution, first of all, we have to identify alpha or level of significance. Then we need to find the degrees of freedom, which is n minus 1. Remember that n is equal to your sample size. N is sample size. Then to find critical value, you have to use t-table because you're working with t distribution. Again, sigma is missing. You don't have your sigma. So you cannot use z-table. You have to use a new table, t-table. Then if you have a left-tailed graph, we use one-tail test and we put a negative sign next to our number. Again, to use t-distribution, we have to identify alpha, level of significance, degrees of freedom. If we have a left-tailed graph, we look at the table, t-table, and we put a negative sign next to the number that we find within the table. If we have a right-tailed graph, no negative sign is needed. If we have a two-tailed graph, then we're going to use two-tailed alpha with negative and positive sign. Let us go over one example to see what's going on here. Find a critical value for a left-tailed test. Suppose your alpha level of significance is 5% and the sample size is equal to 21. Very well. We know that the level of significance is just 5%. We can find the degrees of freedom, which is n minus 1. N is 21. You get 21 minus 1, which is 20. To use our t-table, the degrees of freedom are on the first column, which is 20. And on the first row, you have your alpha. Since you have a left-tailed test, you have your one tail alpha equals to 5%. Then the intersection between these two is going to be your critical value. That critical value is 1.725, and since you have a left-tailed graph, you have to put a negative sign in front of this critical value. Let us move on to the next page. Finding critical value for a right-tailed test. Now suppose you have a right-tailed hypothesis test. It means that your alternative hypothesis, for example, says mu is greater than a number like k. Its opposite, your null hypothesis, says mu is less than equals to k. So this is your hypothesis test. Suppose in this case, you have a right-tailed test with level of significance equals to 1%, and n, or the sample size, is equal to 17. The very first step is to find the degrees of freedom, which is n minus 1. N is 17, so we substitute 17 here, and the outcome is equal to 16. So we look at our t-table. T-table. On the first column, we have our degrees of freedom, which is 16. And on the first row, very first row, you have a one-tailed test with alpha equals to 1%. The intersection between these two numbers is going to be your critical value, which is 2.583. Since it's a right-tailed test, you don't have to put any negative sign in front of your number. So the critical value stays the same. Another example. So we're done with left-tailed graph, right-tailed graph. Now, what if we have a two-tailed graph? Question says, find the critical values for a two-tailed test. So in this case, your hypothesis test is going to be like this. Your alternative hypothesis says mu is not equal to a number like k, so its opposite. Null hypothesis says mu is equal to k. So in this case, your alpha is 10%, level of significance is 10%, and your sample size is equal to 26. First, we find degrees of freedom, n minus 1, 26 minus 1, which is 25. We're looking at our t-table. On the first column, we have degrees of freedom, which is 25. And on the first row, we have a two-tailed test. Two-tailed. Two-tailed alpha equals to 10%. The intersection between these two is a positive number, which is equal to 1.708. Now, since you have a two-tailed graph, you have a negative and a positive critical value, dividing the rejection region and non-rejection region. Very well. How do we use t-test to make decisions about our hypothesis testings? So first of all, we're using t-test for the mean or population mean. The t-test for a mean, mu, is a statistical test for a population mean. The test statistic is the sample mean. The standardized test statistic is x bar minus mu divided by s over square root of n. Remember that if sigma is known, you have to use z-test. x bar minus mu divided by sigma over square root of n, then you use z table. If sigma is missing, if the population standard deviation is missing, you have to use your t-test along with t-table. Very well. Guidelines. First of all, verify that sigma or population standard deviation is missing. The sample is random and either the population is normally distributed or the sample size is greater than equals to 30. Then form your null and alternative hypothesis. Specify the level of significance, alpha. Identify the degrees of freedom, n-1. Then look at your t-table to find critical value or critical values. Then you can identify your rejection region, form your standardized test statistic, then decide if to reject or fail to reject the null hypothesis. Well, let's go over one example to see what's going on. Okay, hypothesis testing using a rejection region. Let us read through this example, find keywords. A used car dealer says that the mean price, so you're working with the mean, of a 2-year-old sedan in good condition is at least, okay, we have a keyword at least, $20,500. You suspect this claim is incorrect. So this is your claim. It is at least. It means that greater than or equal to. When you're talking about at least, the meaning of at least is greater than or equal to. Very well. What's the meaning of that? It means that your null hypothesis is given. Your null hypothesis says mu is greater than or equal to $20,500. So null hypothesis is given. Your job is to form alternative hypothesis, which is the opposite. Mu is less than $20,500. So as you can see, we're done with the hypothesis tests. These are null and alternative hypotheses that we have. Very well. Let's move on, see what's going on, what else is given. You suspect this claim is incorrect and find that a random sample of 14, so 14 is your n sample size, similar vehicles has a mean price of $19,850. This guy is your sample mean. This is your x bar. And your sample standard deviation is 1,084. So S is given. It's not sigma. If you have information about population, you say, hey, I have my sigma, but here you have a random sample of 14 similar vehicles, has a mean price of 19,850, and the standard deviation of your sample S is 1,084. Now, check to see if you have to reject or fail to reject the null hypothesis with level of significance equal to 5%. Is this a z-test? Is this a t-test? Of course, it's not a z-test. To use z-test, you have to have sigma. We don't have sigma here. We only have sample standard deviation, which is S. Very well. So we have to use our test statistic, T. Before finding the test statistic, let us find the critical value. Because your alternative hypothesis is less than, it means that you have a left-tailed graph. Now, the degrees of freedom is equal to sample size minus 1, which is 13, and the level of significance is 5%. So 13, the degrees of freedom, and level of significance, 5%. The intersection between these two is your critical value with a positive sign, 1.771. Since you have a left-tailed graph, you have to put a negative sign in front of it. Okay, so this is your critical value, dividing the rejection region and non-rejection region into two different parts. Let us form our standardized test statistic, T, which is x bar minus mu, divided by s over square root of n. So you have x bar 19,850 minus 20,500 divided by s, which is 1084 over square root of 14. We do the algebra, and our standardized test statistic is negative 2.244. Since negative 2.244 is less than your critical value, it's inside the rejection region. It means that we reject the null hypothesis. That's your conclusion. Again, test statistic, negative 2.244 is less than your critical value, and it is inside the rejection region. So we reject the null hypothesis. So the interpretation, there is enough evidence at the 5% level of significance to reject the claim that the mean price of a 2-year-old sedan is at least $20,500. Another example for you. An industrial company claims that, very well, so here we have our claim. Let's maximize this a little bit. Claims that the mean pH level of the water in a nearby river is 6.8. The mean is 6.8. So what's given? Your null hypothesis is given. It says mean is 6.8. Your job is to find alternative hypothesis, which is the opposite of your null hypothesis. Mu is not 6.8, so you have a two-tailed graph. Rejection regions are on the left and right-hand side. Since your alternative hypothesis says is not equal to, it means that you have a two-tailed graph. Well, you randomly select 39 water samples. So N is 39. Your sample size is given. And measure the pH of each, the sample mean and standard deviation. So sample mean and standard deviation of sample are given. Mean X bar is 6.7 and your S, standard deviation of the sample, is 0.35. Is there enough evidence to reject the company's claim at 5% level of significance? Very well. Since sigma is not given, we're not using Z. We're going to use T table. We formed our null and alternative hypothesis. We know that we have a two-tailed graph. Our job is to find the critical values. Degrees of freedom is equal to 38. Now we look at our T table. Degrees of freedom, 38. And we have a two-tailed graph. So alpha is 5% and it is two-tailed. The intersection between these two numbers give you a positive critical value, 2.024. Since you have a two-tailed graph, you must put a negative sign next to this number. Because of symmetry, you get a negative and positive critical value. So your critical values, negative 2.024 and positive 2.024. Again, the rejection regions are on the left and right hand side. Now, let us check to see if this test statistic is inside the rejection region or not. Perfect. T is x bar minus mu divided by s over square root of n. X bar is 6 minus 6.7 minus 6.8 divided by your s is 0.35 over square root of 39. You do the algebra and your test statistic is negative 1.784. Okay. This number, negative 1.784, it's not less than, it's not on the left side of negative 2.024. It is on the right hand side. It's closer to 0, to the positive side, till to the negative side. So as you can see, this test statistic related to your sample is outside the rejection region. This region is non-rejection region. Left-hand side and right-hand side are rejection regions. Since T, negative 1.784 is outside the rejection region, you fail to reject the null hypothesis. Let us go over the last example in 7.3. So how do we use p-values? For example, suppose you have a Department of Motor Vehicles office claims that the mean wait time, so the mean wait time is less than 14 minutes. So what's given? Your alternative hypothesis is given, because it doesn't have any equality. It says mu is less than 14 minutes. So you can form your null hypothesis. It says mu is greater than or equals to 14 minutes. So there is a random sample of 10 people. So n is equal to 10. Has a mean wait time of 13 minutes. X bar is given. And the standard deviation of the sample is 3.5. S is also given. At alpha equals to 10%, check the claim. Very well, before our null hypothesis, alternative hypothesis. We can find our p-value by finding our test statistic. Test statistic, T is equal to x bar minus mu over s over square root of n. This T is almost negative 0.90. P-value is equal to almost 19%. Is 19% less than 10%? Is your p-value less than or equal to alpha? Of course not. Your p-value is greater than alpha, so you fail to reject the null hypothesis. So what we learned so far? We learned that if you're working with mean, we have two cases. If sigma is given, we have to find z, which is x bar minus mean, divided by sigma over square root of n. If sigma is not given, we have to work with sample standard deviation. We find t, which is x bar minus mean, divided by s over square root of n. I expect you to ask, what if you are working with proportion, not the mean? Very well. Hypothesis test for proportions. Hypothesis tests for proportions can be used when we have like special cases of like counting. When politicians want to know the proportion of their constituents who favor a certain bill, or when quality assurance engineers test the proportion of parts that are defective. If n times p is greater than equals to 5, n times q is greater than equals to 5 for a binomial distribution, then the sampling distribution for p hat is approximately normal, with the mean of p hat is equal to p, and standard error sigma sub p hat equals to square root of pq divided by n. For proportion, we use z-test. The z-test for proportion p is a statistical test for proportion, population proportion. The z-test can be used when a binomial distribution is given such that n times p is greater than equals to 5, n times q is greater than equals to 5. The test statistic is the sample proportion p hat. So for population, we use p itself. For sample, we put a hat on top of it, p hat. And the standardized test statistic is z equals to p hat minus p divided by square root of pq over n. Let's go over the guidelines together. So when it comes to proportion, we're going to use a z-test, not a t-test. First of all, verify that the sampling distribution of p hat is normal distribution. So np is greater than equals to 5 and nq is greater than equals to 5. State the claim. It means that you need to find the null and alternative hypothesis, identify your level of significance, then use z-table to find the critical value or critical values. Then identify the rejection region. After that, you have to find your test statistic, p hat minus p, divided by square root of pq over n. Then you need to decide if this z is inside the rejection region or reject the null hypothesis, or z is outside the rejection region or fail to reject the null hypothesis. Very well. Example 1. Hypothesis test for proportion. So in this example, we have a researcher. That researcher claims that less than 40% of US cell phone owners use their phone for most of their online browsing. Okay, here we have a claim, we have a keyword. What's given? Proportion is given. When you're working with percent, it means that you have proportion. Since you have less than, it means that your alternative hypothesis is given. Proportion is less than 40%. Your null hypothesis says proportion is greater than or equal to 40%. Since it's less than, you have a left-tailed graph. Left-tailed graph. Perfect. Let us continue. In a random sample of 100 adults, so n is given 100, 31% p hat, 31% say they use their phone for most of their online browsing. At 1% level of significance, is there enough evidence to support the researcher's claim? Okay, again, since we have percent, it means that we are working with proportion. proportion. Remember that. Before null hypothesis, alternative hypothesis, let us check to see if the normality is met or not. N is the sample size, 100. P is equal to 40%, so N times P. P is 40%, which is equal to 40. Is this greater than or equals to 5? Of course. N times Q. Remember that Q was 1 minus P. Since P is 40%, Q is 60%. N times Q. N is 100, Q is 60%. 100 times 60% is 60. Is this guy greater than 5? Of course. So the normality is met. Now we can move on to use z-test. First of all, we're going to use our z-table. We're going to use z-table to find the critical value. Alpha is 1%, and we have a left-hand graph. We find 1% inside the table within the numbers, and we find the critical value negative 2.30.03. This is your critical value. This is the number that divides the rejection region from the rest of the graph. Now, for this sample, we're going to use sample test statistic, which is p hat minus p divided by square root of pq over n. P hat is 31% minus p, which is 40%, over square root of p, 40%, q, 60%, over 100. After doing the algebra, our test statistic is negative 1.84. Okay, negative 1.84 is not less than negative 2.33. It's greater than. It's on the other side of the region. Since Z is not inside this blue region or rejection region, we fail to reject the null hypothesis. Fail to reject the null hypothesis. Okay. Let us move on to the next example. A researcher claims that 86% of college graduates say their college degree has been a good investment. Okay, perfect. So 86%, since you have percent, it means that you're working with proportion, and they are saying that 86% of students saying that, hey, the degree is a good investment. Exactly 86% of them. So your null hypothesis is given. P is equal to 86%. This example has given you the null hypothesis. To form your alternative hypothesis, you just write the opposite of it. It means that you have a two-tailed graph. You take a random sample of 1,000 graduates, 845 say their college degree has been a good investment. At alpha equals to 10%, you reject or you fail to reject the null hypothesis. Which case is that? Very well. First, we have to check the normality. N times P. 1,000 times P, which is 86%. After you multiply these two numbers, you get 860, which is greater than 5. So the first condition is met. We're good here. N times Q. N is 1,000 times Q, 1 minus P, 14%. The multiplication is 140. The second condition for normality is also met. Okay, we know that our null hypothesis says the proportion is 86%. Our alternative hypothesis says the proportion is not 86%. Since your alternative hypothesis says not equal to, it means that you have a two-tailed test, two-tailed graph. Rejection regions are on the left and right-hand side. Okay, now alpha is equal to 10%. We have to use our Z table. First of all, since you have a two-tailed test, you have to divide alpha by 2, which is 5%. You look for 5% in your Z table. The matching Z value is equal to 1.60.4. Since you have a two-tailed graph, you have a negative and positive critical value. Okay, next step is to form the sample proportion. Remember, for sample, we use P hat. Compare these two. P is population proportion. P hat is sample proportion. 845 students said it's a good investment out of 1,000. So you do the division to find your P hat. Now we find the standardized test statistic Z, which is P hat minus P, divided by square root of PQ over N. After doing the algebra, our test statistic is negative 1.37. Is this number inside the rejection region? Okay, perfect. We know that the rejection region is on the left-hand side of negative 1.64 and on the right-hand side of 1.64. Negative 1.37 is not inside the rejection region. It's outside the rejection region. So you fail to reject the null hypothesis. You can interpret it this way. There is not enough evidence at the 10% level of significance to reject the claim that 86% of college graduates say their college degree has been a good investment.